All right, today we are going to look at sections 8.9, 8.10, and 8.11, which are going to give us a nice introduction as to how to draw structures for molecules so that we know what the molecules look like. If we know what they look like, we can tell a lot about their properties. Now, the structures of molecules is based upon something called the localized electron model, which is simply this, that molecules are composed of atoms that are bound together by sharing pairs of electrons using the atomic orbitals of the bound atoms. So we know that atoms have these atomic orbitals where the electrons reside, and it is the electrons in those orbitals that are shared between atom and atom that allows them to combine to make a molecule. There are two types of electrons that we need to focus on. We have lone pairs. That's pairs of electrons that are localized on an atom. And then we also have bonding pairs. These are pairs of electrons found in the space between the atoms. I want to make a note here that the term localized, I kind of think of meaning located. So you can think of lone pairs being just electrons located on an atom that aren't participating in bonding. Okay? On the other hand, bonding pairs are electrons that are localized between atoms. So those are the ones that are contributing to bonding. And just to do a quick example of that, if we take a look at the water molecule, which is H2O, it looks like this. H2O has two lone pair electrons that are on the oxygen atom, and those are right here. Okay, boom, 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 boom. And then it also has the two bonded pairs of electrons that are between the oxygens and the hydrogens there and there. Okay? So just think of localized being located. All right. So the localized electron model allows us to do three big things. It allows us to describe the valence electron arrangement in the molecule. That allows us to draw the Lewis structure, which we've done before. It allows us to predict the geometry of the molecule. And that's really important because geometry allows us to dictate polarity. And finally, it allows us to make a description of atomic orbital types used to share electrons or hold lone pairs. So we can actually now get a visual of like where these electrons are now located. That'll be the last section that we talk about in this chapter. All right, let's draw some Lewis structures. Definition of a Lewis structure is just something that shows how valence electrons are arranged among atoms and molecule. It reflects the central idea that stability of a compound relates to noble gas electron configuration. Most of the time that means that we want to form a stable octet. Some of the time, though, that means that we want to form a stable duet. That would be the case of hydrogen. Now, hydrogen has one valence electron. We know that. And it is in the first row of elements. It's just hydrogen and helium up there. And they only need that one valence electron to be shared in order to become happy. And so that's what happens. We get that shared pair of electrons there, and that forms the bond between hydrogen. And if we wanted to draw the hydrogen molecule, we could just simply go H dash H. And that's actually a Lewis structure right there of the hydrogen molecule. There are no lone pair electrons on the hydrogen molecule. Okay? So there's the duet rule. Hydrogen forms stable molecules where it shares two electrons. Now this isn't just with another hydrogen atom. This could be with chlorine, so make hydrogen chloride or hydrochloric acid, or with fluorine, hydrogen fluoride. It's just sharing that one electron, or two electrons, so that it becomes stable. Now the octet rule is a little bit more common, and we're going to use fluorine as our example here. Most elements form stable molecules when surrounded by 8 total electrons. Like I said, fluorine's a nice example of that. So we've got a space-filling model here with fluorine, but that doesn't tell us a lot about what the electrons are doing. So let's draw a Lewis structure to help us show that. We'll just draw 2 fluorine atoms. There's one, and here's the other. I don't know why this one is bigger. Pay no mind to that. Okay, there we go. Now, we know what's going to happen. We have 7 electrons on each atom, so that means there's going to be sharing of an electron between the 2 atoms, and there that sharing is, right there. And that creates the bond between the fluorine atoms, which allows that molecule to be stable. So those are the bonded atoms, and these are the lone pair electrons. Bonded electrons, lone pair electrons. All right. So let's think of some steps for writing those structures. The 2 that we just did, hydrogen and the fluorine molecule, are pretty simple. They do get more difficult, so it's nice to have some steps. Your first thing, you want to sum the valence electrons for all the atoms. So in the fluorine molecule, we have 2 fluorines. Fluorine has 7 electrons total per atom, and so 2 times 7 would be 14. 2, we want to use a pair of electrons to form a bond between each pair of bound atoms. And then third, atoms usually have noble gas configurations, and so we want to arrange the remaining electrons, the remaining valence electrons, to satisfy the octet rule, or the duet rule for hydrogen. Notice we're not using helium, because helium just doesn't bond with anything. Okay, so let's do an example. Let's do water and break it apart. So sum the valence electrons from all the atoms. We get H2 and O. And there we go, there's the sum of all of those. We have 8 total electrons that we need to be wary of. Okay, let's go to step 2 then. Use a pair of electrons to form a bond between each pair of bound atoms. Here we go, we'll do that. Boom, boom. Now you might ask, why is oxygen in the middle? Well, you know oxygen's in the middle for right now. We'll get more to centrally located atoms a little bit later on. And then thirdly, atoms usually have noble gas configuration, with the exception of hydrogen. Let's go ahead and satisfy that. All right, there we go. Okay, and you'll see that we place valence electrons there on the top and the bottom of oxygen. Now, you might say, well, Mr. Cornick, in a previous slide, that your water molecule did not look like the water molecule that's right here. And that's correct. I'm going to say that my water molecule in a previous slide actually was the correct one. And that's because it took something called geometry into consideration. What eventually will happen, as we will see later on in this chapter, these electrons actually push the bonds downwards. Okay, they push the bonds down, push the hydrogen atoms down, making a bent molecule, giving water its polarity, and thus all of its very, very cool properties. All right, so there's water. Let's take a look at the other 2 examples we have on here. PBr3, okay, so that's phosphorus tribromide. And then the last one, HCN. Maybe you can go ahead and do HCN by itself. That's hydrogen cyanide. Horribly deadly stuff, by the way. And there it is. You'll notice that nitrogen often forms triple bonds because it has 3 single electrons. Let me show you just for a second what that looks like. Here is nitrogen if it would be all by itself, which it oftentimes is not, right, because it is a diatomic. But we can see with its 3 unbonded electrons that it's pretty darn aggressive in forming those triple bonds. All right, let us move on. Let's do a little concept check here. I'm going to have you draw a Lewis structure for each of the following molecules. See if you can get that right. Go ahead and pause it and give it a shot. All right. Let me just show you the ammonia. So you've got nitrogen. Okay, how many electrons total? Let's see, nitrogen's got 5. Each hydrogen has 1, and we have 3 hydrogens, so let's do the total there. I think that's 8 electrons. Now, centrally bonded atom. Which one's in the middle? Well, it's usually the one that's least abundant, and in this case, that is going to be nitrogen. Toss the hydrogens around the nitrogen. Okay, remember we need 8 total electrons. Here we have 2, 4, 6. Are the hydrogens happy? You bet they are. They all have 2 electrons, and so those final 2 valence electrons have to go there and there on the nitrogen. Boom. All right, try carbon dioxide and carbon tetrachloride, and I'm sure you can handle those on your own. All right, last section then for this video is the exceptions to the octet rule. Every rule has some exceptions, right? So we have to take a look at those, and this usually isn't addressed in a traditional chemistry class, but you are AC chemists, and you are geniuses, so we can go this far. So there are a couple elements that are a little goofy. Boron tends to form compounds in which the boron atoms have fewer than 8 electrons. So less than 8 electrons. My goodness, that's crazy. It does not have a complete octet. Okay. Let me just quickly write out the electron configuration for boron here. 1s2, 2s2, 2p1. Okay, and if we write the orbital diagram just for those valence electrons, here's the 2s, and here's the 2p with that 1 valence electron. All right, so we're often going to see that it does not fill up the total p sublevel, okay, that it leaves it a bit empty or half full. Okay, so let's take a look at boron here. Let's get an example. Here's BH3, boron trihydride, okay, with 6 electrons. Okay, if we count them out, let's do that. Let's count them out. Boron, how many valence electrons? 3, right? Boron equals 3 electrons. Hydrogen, 1 electron times 3, 6. Okay, we bind them all together. And when we do that, we find out, oh my goodness, there's only 6 electrons in boron. All right? Only 6 electrons. So that is a very, very rare but common, I guess, for that atom exception to the rule. Now, there are some elements where it's necessary to actually exceed the octet rule. Okay, for one of several third row or higher elements, place the extra electrons on the central atom. So you're going to see this oftentimes with phosphorus, sulfur, chlorine, and then atoms that are actually larger than that do this very often. And you might be able to recognize why, because atoms that are larger than that have a d sublevel. And those d sublevels have a lot of different orbitals that they can toss electrons into, 5 to be exact. So let's look at one SF4 sulfur tetrafluoride, 34 total electrons, and arsenic pentabromide with 40 total electrons. And let's take a look at their configurations. Look at how crazy these are. And that central atom there has 2 extra valence electrons, taking in consideration the rule that we just had up here. Here's the 2 extra. Here's the 2 extra valence electrons. Okay? Big old molecules. The reason why they can actually have those extra valence electrons is because they're larger atoms, so those extra valences can reside further away from the nucleus. There's less electron density, so those electrons do kind of fit inside the atom. All right, last slide. Here's kind of a synopsis of violations to the octet rule. Write this down. You might want to write some of these guys on note cards to study them, and you might have to commit some to memory. Violations to the octet rule usually occurs with boron and elements of higher periods in most nonmetals. Common exceptions to the octet rule are the following: beryllium, boron, phosphorus, sulfur, xenon, chlorine, bromine, and arsenic. So you might ask yourself, how do you know if it's an expanded octet? Because, Mr. Cornick, this is chemistry class. We don't like memorization. There's 8 elements to memorize right there. That's not great. So how do we know? Well, here's a couple of ways to figure that out. First of all, there are more valence electrons than the initial drawing. Second of all, there are more than 4 bonds to any one atom. And third of all, formal charge doesn't work out with just 8 valence electrons. Formal charge, oh, that's a new term right there. And I'll tell you what, we are going to focus on this term, formal charge. Boy, that was supposed to be an underline. Formal charge. We'll focus on that term tomorrow in class. So let's look at the first 2. Here's BF3. This is not boron trihydride, this is boron trifluoride. This is what it would look like. Okay, and if we counted all the electrons, that would actually be the total number of valence electrons. And so we said boron and beryllium are very often exceptions to the octet rule. And we call these incomplete, right? Because they don't have 8 electrons to that central atom, to any one atom, right? So boron is the incomplete atom. What about exceeding the octet rule? Well, sulfur tetrafluoride is a great example of that. And we call these expanded octets. So phosphorus, sulfur, and xenon do a great job of expanding their octets. And if you look at the molecule here on the right side of the page, kind of interesting because it's actually showing molecular geometry. if you just simply look at this molecule and say, well, Cornick, hold on. SF4, this works. Okay, there are 4 bonds to the central atom. 1, 2, 3, 4. That's 8 electrons. These are all fluorines up here. That's a fluorine, that's a fluorine, that's a fluorine. So that, like, each fluorine has these 6 lone pair electrons, has the bond, boom, that's 8 electrons. But look at the geometry of the actual molecule. Notice how it looks a little weird. Doesn't it seem like most of the fluorines, if not all of them, are bending downwards? I wonder why that is. Why are there no fluorines over here? Simply because there's an extra pair of electrons on that sulfur atom that are forcing the fluorines away. Remember, electrons don't like each other. Okay, that's 9, 10, and 11.